Welcome to This Explainer. Today, we're diving headfirst into the fabric of perspective, a guide to relative motion. We're going to take those foundational, everyday concepts of space and time that we completely take for granted, and we're going to push them to the absolute limits of the universe. Honestly, by the time we wrap this up, you will never look at a simple train ride the exact same way again. So let me ask you, are you actually sitting still right now? Take a second and really think about it. Because, well, even if you're just lounging on the couch right now, you are currently hurtling at tens of thousands of miles per hour relative to the sun. And to make it even crazier, our entire solar system is swirling around the Milky Way at an even more staggering speed. If you feel stationary right now, it's literally just because of your perspective. To actually make sense of this, we need a foundational concept, the reference frame. Think of it as a coordinate system bundled together with the clock. Basically, it just tells you where and when things happen. The absolute bedrock truth of physics is that motion is never absolute. It is always, always relational. I mean, there is no giant cosmic billboard pinned somewhere in the void of space that says, hey, this point right here is truly, absolutely at rest. No, every single measurement of motion you make requires a benchmark. Okay, let's dive into this a bit deeper. For centuries, early physicists built their theories on a very human, very comfortable illusion, the idea of absolute space and time. Isaac Newton literally built all of classical mechanics back in the 17th century, assuming that space was just this fixed, immovable background. He thought time ticked away at the exact same rate for everyone, everywhere in the cosmos. And, at the time, it felt perfectly logical. But our understanding evolved dramatically over the centuries. Way back in 1632, Galileo described an experiment happening inside a sealed ship cabin, down below deck. He realized that if the ship was gliding smoothly, water dripping or butterflies flying around inside would look exactly the same as if the ship was just sitting docked at the port. You literally couldn't tell if you were moving. By 1687, Newton mathematically formalized all this. But then, 1887 hit, and we had a total crisis on our hands. Physicists back then thought light needed a stationary medium to travel through, which they called the ether. But the famous Michelson-Morley experiment entirely failed to detect any sort of ether wind as the Earth moved. The speed of light just stubbornly refused to change, no matter which direction the Earth was flying. That massive puzzle set the stage for 1905, when a young Albert Einstein triggered a complete paradigm shift. The contrast between these two realities is honestly night and day. In classical physics, time is universal, and you can just keep adding up velocities forever. Like if you shoot a bullet forward from a moving train, the bullet's total speed is the train speed plus the bullet speed. Simple, right? But Einstein totally shattered those classical rules. Under his special relativity, time is relative, and the speed of light is a hard, absolute cosmic speed limit. If you shine a flashlight from that same moving train, the light doesn't travel at the train's speed plus light speed. It just travels at the speed of light, period. Einstein actually built this massive 1905 theory on just two basic postulates. The first one, that the laws of physics are the same in all non-accelerating frames, was really just an update to what Galileo was already saying. But the second one, that's the radically brilliant part. The speed of light is constant for all observers. To make the math on that work, to ensure light is always traveling at roughly 300,000 kilometers per second for literally everyone, space and time can no longer be separate things. They have to stretch, they have to squeeze, they become completely entangled into one unified thing, space-time. Which leaves us right to the relativity of simultaneity. Imagine a super long train moving at high speed past a station platform. Suddenly, lightning strikes both the front and the back of the train at the exact same moment, at least according to a guy standing still on the platform. But think about a woman standing exactly in the middle of that moving train. She's rushing toward the front strike and moving away from the rear one. Because she's moving, the light from the front lightning bolt hits her first. So to her, the front lightning definitely struck before the rear lightning. And here is the absolute kicker. Neither of them is wrong. There's literally no universal now. Two events can be perfectly simultaneous for one person and happen at completely different times for somebody else. And if that isn't weird enough, this entanglement of space and time means that moving clocks literally run slower and moving objects physically shrink along their direction of motion. And we're not just talking about abstract theory here, it's an undeniable reality. Take cosmic ray muons. These are subatomic particles created 15 kilometers up in our atmosphere. They have such an incredibly short lifespan that they really should decay after traveling just 650 meters. Yet they routinely survive the whole trip and hit the Earth's surface. How is that possible? Well, from our perspective down on Earth, The muon is traveling so amazingly fast that its internal clock ticks much, much slower. That's time dilation. But from the muon's perspective, its clock feels completely normal, and instead that 15-kilometer chunk of Earth's atmosphere physically shrinks down to just 650 meters. That's length contraction. To really put that into perspective, let's look at the number 70.7. This is the Lorentz factor for a specific extreme speed, acting as the mathematical core of relativity. If you were somehow able to travel at 99.99% the speed of light, your time literally slows down by a factor of over 70 compared to someone just standing still. That means for every 1 year you experience on your journey, over 70 years would pass for every single person you left back home. Which naturally brings us to the famous twin paradox. Let's just walk right through it. Step 1, one twin leaves Earth on a super fast rocket, while the other stays home. Now, since motion is relative, the twin in the rocket looks back and thinks the Earth twin is the one moving away and is therefore the one aging slower. Step 2, the rocket twin turns around to head back home. And step 3, they finally reunite. Now, you might be wondering, if everything is totally relative, how can one of them be truly older? The secret is in that second step. The traveling twin has to fire their engines, heavily accelerating and decelerating to make that U-turn. That acceleration creates a non-inertial frame. It completely breaks the symmetry. Because they experience that physical acceleration, when they reunite, the traveling twin is genuinely, biologically younger than the twin who stayed on Earth. So, that was 1905. Let's fast forward to 1915 and see how this evolves from special to general relativity. You see, Einstein wasn't quite done yet. He realized his earlier theory only worked for things moving at constant, steady speeds. But what about acceleration? And what about gravity? His monumental breakthrough here was realizing that gravity isn't this mysterious, invisible force pulling objects across empty space like we always thought. Not at all. Gravity is actually the geometry of the universe itself. It is the literal curvature of space-time, completely warped by the presence of mass and energy. The absolute key to unlocking this was something called the equivalence principle. Einstein imagined putting a person inside a sealed, windowless elevator box. Imagine that box is just floating out in deep, empty space, but it's being pulled upward by a rocket at exactly 9.8 meters per second squared. The person inside feels their feet pressed firmly against the floor. Now, take that exact same box and just place it entirely stationary on the surface of the Earth. They feel the exact same thing. Einstein realized there is literally no physical experiment you could possibly do inside that box to tell the two scenarios apart. Uniform acceleration and gravity are locally the exact same thing. Because gravity is just curved geometry, objects moving through space are simply following geodesics. A geodesic is just the straightest possible path through a curved space. Think about it. The Earth isn't reaching out with some invisible tether to pull the moon. The moon is literally just rolling along a curved dip in space-time created by Earth's heavy mass. It gets wilder too. Because space-time is curved, even starlight bends when it passes around massive objects, a really cool effect we call gravitational lensing. And perhaps most mind-blowing of all, gravity itself slows down time. A clock sitting on the surface of the Earth ticks ever so slightly slower than a clock floating way up in deep space. Now, you might be wondering, okay, this is some fascinating cosmic philosophy, but what does it actually have to do with me? Well, these exact 100-year-old esoteric physics equations are literally the foundation of how your modern technology functions. We are taking this straight from the deep cosmos right into your pocket. Take exactly 38 microseconds. That is the exact daily time discrepancy between the GPS satellites orbiting our planet and the receivers down here on Earth. Remember how we said moving clocks run slow? Well, those satellites are moving incredibly fast, so special relativity dictates their clocks should run slow. But they are also high up in weaker gravity, so general relativity dictates their clocks should run fast. When you combine those two competing effects together, the satellite clocks end up running exactly 38 microseconds faster every single day. If engineers didn't program Einstein's relativity equations into the GPS network to constantly fix this, the navigation on your smartphone would drift and be completely off by 10 kilometers every single day. There's just no way around it. And it doesn't stop with GPS. The applications are everywhere, making it a real game changer across multiple domains. In medicine, when a patient gets a PET scan, the machine is detecting gamma rays created by antimatter annihilating with matter, relying directly on Einstein's famous E equals mc squared. In advanced navigation for things like aircraft and submarines, fiber optic gyroscopes measure rotation by splitting light beams and relying on the relativistic Sagnac effect in rotating frames. And of course, in particle physics, the massive accelerators over at CERN literally could not function or even be built without heavily accounting for the fact that particles gain relativistic mass as they push closer to the speed of light. Now, what's really interesting here is what happens when we zoom all the way down to the subatomic level. Welcome to the quantum frontier. We've talked a lot about how relative motion works for giant massive stars and super fast trains. But the unresolved boundary between general relativity and quantum mechanics, that is one of the most active, exciting battlegrounds in all of modern science right now. Researchers are literally rewriting the rules as we speak. Brand new discoveries coming out of 2025 and 2026 regarding quantum reference frames, or QRFs, are showing some massive leaps. For instance, a team spanning Vienna and Brussels proved that transforming between quantum frames actually requires an extra particle subsystem just to carry the relational properties. And research out of Qatar late last year demonstrated that changing your reference frame at the quantum level physically transforms simple local operations into complex entangling ones. By early 2026, scientists were introducing completely new anisotropic preferred reference frames directly into relativistic quantum information theory. Basically, they're proving that a quantum operation actually physically transforms based entirely on the internal reference frame of the observer. Which leaves us with this final, incredibly provocative thought. As we've seen today, there is absolutely no absolute background to the universe. Everything is relative to the observer. But what happens to reality when the observer, the reference frame itself, the very clock or ruler being used, is in a quantum superposition? It's a question that completely challenges our understanding of existence, and it clearly signals the next great revolution in physics. Thank you so much for exploring the fabric of perspective with us in this explainer today. Stay curious.